Welcome to lecture series on EPG Padasala for Computer Science. Today's lecture we will be discussing software quality metrics. First, I will be presenting an overview of metrics in real life, and then we will move into use of metrics in the software development life cycle. The learning objectives are: outline the need for software metrics, give a basic understanding of why and how we measure, address how measurement can be used for assessing software quality, outline how metrics are used for evaluating the effectiveness of techniques and tools. Measurement. Measurement is common and necessary practice for understanding, controlling and improving our environment. Measurement is the process by which numbers or symbols are assigned to attributes of entities in real world to describe them according to well defined rules. How we use measurement? As an example, in the shop we can compare the price of one item with another. In the clothing store we contrast sizes. Clothing size may be small, medium or large. In our journey we compare distance travelled to distance remaining. Measurement and calculation. Measurement is a direct quantification. For example, measuring the height of a person. In any measurement activity, rules are to be followed. The rules help us to be consistent in our measurement as well as providing a basis for interpreting data. Measurement theory tells us the rules, laying the groundwork for developing and reasoning about all kinds of measurement. The representational theory of measurement seeks to formalize our intuition about the way the world works. The data that we obtain as measures should represent attributes of the entities we observe, and manipulation of data should preserve relationships that we observe among the entities. Our intuition is the starting point for all measurement. In real world, when we see two people, we observe that one is taller than the other without actually measuring them. Given any two people x and y, we can observe that x is taller than y is taller than x. Therefore, we can say that taller than is an empirical relation for height. Calculation is indirect. We take measurements and combine them into a quantified item that reflects some attribute whose value we are trying to understand. For example, payable income tax of an employee is calculated using formula that consists of a number of factors such as taxable income, professional tax paid, house rent allowance, savings, donations, etc. The valuation is a quantification, not a measurement, and its expression as a number makes it more useful than qualitative assessment alone. Measurement and prediction. A prediction system consists of a mathematical model together with a set of prediction procedures for determining unknown parameters and interpreting results. Suppose we want to predict the cost of a journey by a car from Chennai to Trivandrum. We begin by obtaining measures. Let A denote the distance between Chennai to Trivandrum, B denote the cost per liter of fuel, and C denote the average distance we can travel on a liter of fuel in our car. We can predict the journey's cost by using the formula cost is equal to A into B by C. Software metrics. Measure quantitative indication of the extent, amount, dimension, capacity or size of some attribute of a product or process. Measurement, the act of determining a measure. Metric, a quantitative measure of the degree to which a system, component or process possess a given attribute. Indicator, a metric or a combination of metrics that provide insight into the software process, a project or the product itself. We are familiar with the software development life cycle. Irrespective of the life cycle model used, the umbrella activities include system analysis, system design, coding, testing. Once testing is complete, the product is deployed and the product enters into the maintenance phase. In each phase of the software development life cycle, metrics are involved. Consider the analysis phase, where the deliverable is a software requirement specification document. When the analysis team is preparing the software requirement specification document, considering the functional requirements, there may be a change in the requirements. The client initially would have given a set of requirements. Over a period of time, before the SRS is complete, there may be change in requirements which has to be measured. Once the system analysis is complete, we enter into the design phase, where first we perform the architectural design and second detailed design. Architectural design, we identify the modules and relationship among the modules. Detailed design, we address how each module is to be implemented, what data structures you are going to use, what algorithms you are going to use, whether you are using an existing data structure, whether you are modifying the existing data structure, whether you are using an existing algorithm or you are modifying an existing algorithm. All these issues will be addressed during your detailed design phase. When you are in your design phase, there may be a change in requirement. When there is a changing requirement, sometimes there may be a need to modify your design. Some cases you may have to modify your data design. Some cases you may have to modify your algorithms alone. Once design is complete, you enter into your coding phase, where the design is translated into code. When you are in the coding phase, again, as I have mentioned, there may be a change in requirement which requires modification in design and modification in code. Once coding is complete, you enter into the testing phase. When you are in testing phase 2, there may be changing requirements. So, at each phase of the software development life cycle, you need metrics to measure. Once the product is deployed, the product enters the maintenance phase. In maintenance phase, undetected bugs may be detected and corrected. Changing requirements may be addressed. So, during the evolution of the software, we encounter changing requirements. Thereby, I have stated, depending upon the phase you are, changes has to be made in the work which you have completed. You need to maintain what changes are incorporated, how many requirements have changed, what is the impact of requirement change on design, what is the impact of requirement change on the coding you have done. So, metrics play a major role in each phase of the software development life cycle, and ultimately the quality of the software product. A software metric is a standard of measure of a degree to which a software system or process possesses some property. Why do we measure? To indicate the quality of the product, to assess the productivity of the people who produce the product, to assess the benefits derived from new software engineering methods and tools, to form a baseline for estimation, to help justify requests for new tools or additional training. When a software project is initiated, you start with feasibility study, where we talk about technical feasibility, economical feasibility and operational feasibility. Here too we use measurements. Only if the outcome of the feasibility study is yes, you can go ahead with the project starts. Otherwise, you may not go ahead with the project. This is common for both software projects and other infrastructure projects. SMART: specific, measurable, achievable, required, time constraint. How do I evaluate these? Specific, measurable, achievable, required and time constraint. I need appropriate measures to do that. If I do not adapt appropriate measures, sometimes you may not be in a position to achieve your goal. There may be schedule slippage. Ultimately, you may not be able to deliver a quality assured software product. Types of metrics: process metrics, product metrics and project metrics. Process metrics are measures of the software development process, such as overall development time, type of methodology used. When you consider overall development time, you have resources coming into picture. When I talk about resources, human resources, hardware resources, software resources and others. Others include your environment. So, with respect to the available resources, you may have to compute your overall development time. And when you are computing your schedule, you fix milestones, which are targets of achievements. You measure whether you have achieved each milestone. If you have not achieved, you will have to perform a what if analysis and analyze why you have not achieved. Probably recalculate the time or try to measure how you can complete the project in time by adding additional resources. Process metrics are collected across all projects and over long periods of time. Why I state process metrics are collected across all projects is the prior experience gained in a project may serve as a roadmap for future projects. To be more clear, the bitter experiences you have experienced in prior projects may help you to correct it when you go for a new project. The intent of process metrics is to provide indicators that lead to long-term process improvement. Software process metrics and software process improvement. To improve any process, the rational way is measure specific attributes of the process, derive meaningful metrics from these attributes, use these metrics to provide indicators. The indicators lead to a strategy for improvement. How to measure effectiveness of a software process? We measure the effectiveness of a software process indirectly. We derive a set of metrics based on the outcomes that can be derived from the process. Outcomes include errors uncovered before release of the software, defects delivered to and reported by end users, work products delivered, human effort expended, calendar time expended, conformance to schedule. Project metrics. Project metrics are the measures of software project and are used to monitor and control the project. They enable a software project manager to minimize the development time by making the adjustments necessary to avoid delays, potential problems and risks, assess product quality on an ongoing basis and modify the technical approach to improve quality. Metrics collected from past projects are used as a basis from which effort and time estimates are made for current software project. As the project proceeds, actual values of human effort and calendar time expended are compared to the original estimates. A comparison can be performed only if measurements are done periodically. Once the comparison is done, what if analysis has to be done if you have deviated from the schedule. The what if analysis you have performed may help you in future projects. The data can be used by project manager to monitor and control the project. Product metrics are measures of the software product at any stage of its development, from requirements to installed system. Product metrics may measure the complexity of the software design, size of the final program, number of pages of documentation produced. Direct and indirect measurement. Direct measurement of attribute of an entity involves no other attribute or entity. For example, length of a physical object can be measured without reference to any other object or attribute. On the other hand, density of a physical object can be measured only indirectly in terms of mass and volume. We use a model to show that the relationship among the three is density equal to mass by volume. Direct measures commonly used in software engineering. Length of source code measured by lines of code. Duration of testing process measured by elapsed time in hours. number of defects discovered during the testing process measured by counting defects, time a programmer spends on a project measured by months used. Indirect measures commonly used in software engineering: programmer productivity, lines of code produced by person months of effort; module defect density, number of defects by module size; defect detection efficiency, number of defects detected by total number of defects; requirement stability, number of initial requirements by total number of requirements; test effectiveness ratio, total number of items covered by total number of items; system spoilage, efforts spent fixing faults by total project effort. These are a few examples for indirect measures commonly used in software engineering. Metrics for design, cohesion and coupling. We always follow a divide and conquer strategy. Once the software requirement specification document is complete, we enter into the design phase. As I have mentioned, design can be architectural design or detailed design. We follow a divide and conquer strategy. In software engineering terms, I can state that we identify the modules and relationship among the modules. A module performs a well defined task. Module has a input, process logic, output. The output of a module will serve as an input to another module. Modules can be individually tested. Modules can be reused. So, I can state that the deliverable in the architectural design is modules and relationship among modules. Functional independence. Each module addresses a specific subfunction of requirements and has a simple interface when viewed from other parts of the program structure. Independence is measured using two qualitative criteria named as cohesion and coupling. Good design has high cohesion and low coupling. Cohesion, measure of degree of interaction within a module, measure of the strength of the association of the elements inside a module. As I have mentioned, a module performs a well defined task. When I state a module is highly cohesive if it performs exactly one task. Functionality inside a module should be so related that anyone can easily see what the module does. Goal is highly cohesive module. Coupling, measure of degree of interaction between the modules, measure of interdependence of modules. Goal is to have so little coupling that changes can be made within one module without disrupting other modules. If the coupling among modules are high, there will be ripple effects when a change is done in one module. When I mean a ripple effect, change of code in one module may have an adverse effect on another module. This affects the correctness of the program under maintenance. As I have mentioned already, during your maintenance phase, there may be changing requirements. When there are changing requirements, you may have to modify the design, you may have to modify your code. So, when I talk about modifying the design, you may have to modify your underlying data structure or database. So, your application programs that access the database must also be altered. The procedures, functions may have to be changed. If the coupling is high in one module, it affects other modules also. So, at this point of time, maintenance becomes a tedious process. You may incorporate a functionality in a particular module. The module where you have made the change may work fine. However, the ripple effect may be in another one module. The change in a module may sometimes affect other modules, thereby the correctness of the program is affected. So, the goal is to have high cohesion and low coupling. Qualitative metrics and quantitative metrics. Software metrics can also be classified as qualitative and quantitative. Examples for qualitative: completeness of documentation, tool adequacy; quantitative, execution time, lines of code. Documentation also plays a major role. Why? The analysis team would have prepared the software requirement specification document, which is a legal contract between the client and the developer. From the requirement specification document, the design team would have arrived at a design. Then the coding team translates the design into a workable program. Testing is done by the programmer as well as by a independent test group. To test the product, the independent test group must be clear with the functional requirements. Only by referring to the software requirement specification document, test cases for each functional requirement will be prepared. The developed product will be tested. Bugs, if any detected, will be documented. Once testing is complete and the product is a quality assured software product, it is deployed. You can infer that during each phase of the software development life cycle, appropriate documentation has to be maintained. Once the product is deployed, the product enters the maintenance phase. When the product is in maintenance phase, there may be a circumstance where the human resources involved during the development life cycle are no more with the company. They would have shifted to some other companies, and the team which is going to maintain the software project should understand the functional requirements first. Going through each line of code and understanding the functional requirements is a tedious process. Instead, if appropriate documentation is available, the maintenance team can refer to the documents. Then they can address changing requirements or bugs, if any, detected. We are aware that prior to design, from the functional requirements, we prepare analysis models like data flow diagrams, entity relationship diagrams, use case diagrams, sequence diagrams, deployment diagrams. If these models are documented appropriately, the human resources in the maintenance team will be able to go through the documentation and make changes, if any, that are required during the maintenance phase. Software metrics provide a way to assess the quality of internal product attributes, thereby enabling a software engineer to assess quality. Metrics provide the insight necessary to create effective analysis and design models, code and thorough tests. Metrics not only play a major role in software engineering, they play a major role in real life and in other infrastructure projects too. The critical problems encountered in the development of software system include the estimated costs for development and operation are overrun, the deliveries are delayed, and the systems once delivered do not perform adequately. Use of appropriate metrics in the software development life cycle can overcome the above mentioned problem. I acknowledge the authors of the books which I have referred and the web resources I have used for this presentation. References. Thank you.